Hello, my name is Juan Bensadon, and this is Bootstrap Your Own Latent. I will first explain the problem that the paper is trying to solve, then look at the method it proposes, then the results obtained, and finally describe my conclusions on it. First off, the problem. Image representation learning is the task of training a neural network to take an image and generate a representation of it that will be useful for other tasks, such as object detection, image segmentation, or any other number of learning problems. One of the main ways of training the network in an unsupervised manner is the following. We take an input image, we create many augmented versions of it, which means making modified versions like cropping the image, rotating it, flipping it, etc. And then train the network so that every different augmentation of the same image, as well as the original image itself, yields the same representation after we put it through the network. The problem with this approach, as I just described it, is that the network can simply map all the input images to the to the constant value. And so the loss will be minimized, even though the constant value would not be useful at all for representing different images. To prevent this, we add to the training something called negative samples. This is, aside from the original image and its augmentations, we add images that should yield very different representations. And we train the network to maximize the distance between the representation of these images versus the original image. This works, but finding appropriate negative samples for training is not always easy. It is not always clear which negative samples are better for training, and the whole problem would be simpler if we didn't need them at all. This is where Bootstrap Your Own Latent comes in. We will look at the architecture and how it works to eliminate the need of negative samples. We first take an image X and generate two different augmentations of it. That is a random crop, a flip, etc. These are going to be named V and V prime. These are sent through two different neural networks, one called the online network on top and the other one called the target network on the bottom. We send both augmentations through the encoder F on both networks, which will generate a representation. Now, one of the most important parts of the architecture is that the weights of the second network are an exponential moving average of the weights on the online networks. So the actual parameters that we learn are only those on the online network. The other ones are sort of copy. After obtaining the representation, we first put it through a projector G, which will reduce the dimensionality. And then finally, the online network will have a predictor Q theta, which will try to predict the representation outputted by the target network. The loss function is the following, which essentially means minimizing the distance between what Q theta of the online network predicted and what the target network actually outputted. As I mentioned, the only weights that are kept after each training step are the ones on the online network. The weights of the target network are a moving average of these weights, which is a key component of why it works. As for the results obtained, the paper includes a plethora of benchmarks. These are just some of them. We can see that Bootstrap Your Own Latent outperforms other unsupervised image representation learning algorithms and even comes close in performance to supervised learning algorithms. For some benchmarks, the authors didn't just take the results given in the papers of the other networks, but actually reproduced the networks with their own hardware to give the comparison more fairness. And in general, the results still show good performance for Bootstrap Your Own Latent. Now on to the conclusions. This is a very interesting paper. Conceptually, eliminating the need for negative samples is extremely useful, and the thoroughness of the benchmarking was very good. But there are a couple of caveats that make this paper dubious in its usefulness as it is right now. In the first place, the paper is not fully clear as to why the network does not converge to the optimal solution of constant representation for all images, although the authors do present a couple of hypotheses for it. Secondly, the ResNet 50 version of the network, which is the one used for the benchmarks, needed to be trained during 8 hours using 515 TPU v3 cores, which is a lot of computing. This is not performant at all, and therefore the cost of training would seem to overshadow the problem of finding negative samples. And finally, the pseudocode provided in the annex does not seem like enough to reproduce the results of the paper. So for now, it's more of a proof of concept than an actually usable architecture. That was it. Thank you very much for watching.